Picking up where we left off with polynomial equations. Polynomial equations. If two polynomials are equal, if and only if they have the same degree and corresponding terms have equal coefficients. Okay? We use this to help us equate coefficients when we don't know them. Okay, so that's when you have like an ax squared instead. Okay, you can see from this example that's also on the board. If x squared minus 2x squared plus 3x plus 7 is supposed to be equal to this other cubic function, where a, b, and c are elements of real numbers, then of course we know that a will be 1, b will be negative 2, c will be 3, and d will be 7. Of course, it's never that simple, okay? But you use basically the fact that if they are indeed equal, you can use some algebraic processes to help you find those coefficients. Okay? So we're going to look at some examples that relate to that in polynomial functions. And at that point, you'll be able to finish up the rest of that homework. Okay? Yay! So, we're going to find constants a, b, and c given that 4x to the third plus 10x squared minus x plus 15 is equal to the factored form over there for all x. When it comes to finding the constants, and you know that these two polynomials are to be equal, the easiest thing would be to go ahead and FOIL out that right side here. Okay, or not FOIL, multiply this right side. So x times ax squared is what? Ax cubed. And then x times bx, bx squared. X times c plus 3 times ax squared. 3ax squared, keep going. 3bx plus 3c, okay? So once you multiply that out, you definitely want to combine any like terms, okay? Well, ax to the third, there's no other x to the thirds in this expansion. However, we do have a bx squared and a 3ax squared, and even though we can't add them together and say this is 3abx squared, we can write it as 3a plus bx squared. Like so. It's almost like taking out that common x squared and adding those two together. We can do the same thing with our x's, and this would be 3b plus c x, and then the last one will be just your 3c. You could have also done it with synthetic division, yes. Alright? Since they do equal each other, you know that your 4x to the third needs to be what ax to the third is equal to. So a is equal to 4. Okay? You know that 10 needs to be equal to 3a plus b. And since we know that a is already 4, this becomes 10 equals 12 plus b. So b will be equal to negative 2. And then we have 3b plus c would be equal to negative 1. Or we could do 3c has to be equal to 15 because that's our constant. What is c? C is 5. It would be the same thing that we would get here if we had plugged in b. That would have been negative 6 plus c equals negative 1. And then c would be 5. So then you find your constants a, b, and c. Yes, you could have done this also using synthetic division. Okay? Okay. But what about this type of problem?
I have a feeling we're not going to be able to do this one with synthetic.
Are you going to be able to divide that using synthetic?
No. That looks spooky.
So then that's why the other way that was done for like the last example would be helpful. Okay? So, you're trying to find constants a and b if you know that z to the 4th plus 9 needs to equal this. Okay? So we want to multiply this out. Z squared times Z squared is
Z to the 4.
all right. So we have Z to the 4th plus BZ squared plus cubed plus 3Z squared. When I multiply AZ times Z squared, that becomes AZ cubed plus ABZ squared plus 3AZ. Then when you multiply the 3, that gives you another 3Z squared plus 3BZ plus 9. When you add this all together, this will give you Z to the 4th plus A plus B Z to the 3rd plus AB plus 6 Z to the 2nd plus 3A plus 3BZ plus 9. So, to find the value of A and B, you know that this particular term right here is nowhere in the original part, that's Z to the 4th plus 9. So that means that A plus B has to be equal to what number?
0.
0. That means that AB plus 6 has to be equal to what?
0.
Because there's no square term either. That means that 3A plus 3B has to be equal to
0.
because there's no Z term either. Okay? But we can use these equations to basically solve for A and B. You can do this using substitution. If I solve for A for this equation, I could plug in a negative B for A into this problem. So this becomes negative B times B plus 6. Then I can solve this. This would be negative B squared plus 6 equals 0. 6 equals B squared. So then B is equal to what value? Careful. Plus or minus. So I have two values for B, a positive square root of 6 and a negative square root of 6. Okay? So if B is equal to a positive square root of 6, and I plug it in here, that means that A would have to equal a what? A negative square root of 6. Because I plugged that square root of 6 in, it becomes a negative. But if B was the negative square root of 6, then A would be a what? Positive square root of 6.
So it would be both.
So it would be both. And these would be your solutions.
That's fun.
That's funky.
Questions? Let's do one more. I gotta start this problem.
Can you just multiply 2x plus 3 and x minus 1?
Okay, start out by multiplying the two factors. FOIL. This gives me 2x squared plus x minus 3. Okay, so that gives me a quadratic. I need a quartic. So that means that these two factors need to technically be multiple. These two factors that form a quadratic would technically need to be multiplied to another quadratic. Now, interestingly enough, 2 is the leading coefficient of this polynomial. Exactly. You know that quadratic and the other quadratic has to have a coefficient of 1, so you know that's x squared. And you also know that the constant for this first quadratic is a negative 3. Our constant over here is a positive 3, so that means automatically a negative 1. But it really is that middle term that we don't know, that we can't figure out. So what we're going to do is we're going to substitute in another variable. And then we'll use that to help us multiply it out to set the terms equal to each of the coefficients. Okay? So let's multiply 2x squared plus x minus 3 by an x squared plus cx minus 1. You guys go ahead and multiply that out and give me that, whatever that polynomial is. What you guys get for the polynomial?
2x to the fourth plus, in parentheses, 2c plus 1 to the third, yeah, x to the third, and then plus -5 plus c.
We'll do it the other way.
Okay,
That's
and
fine.
then x squared minus x, well, yeah, minus x, and plus 3.
There's no other x?
There's a regular, like a negative x.
So there's no other like term that has an x in it?
There should be a negative 3 at x, cx.
It's a negative 3cx. So yeah, so when we multiply this 3 by here, we'll have a negative 3cx, and then there was also a negative 1x. So what will that be? Well, a negative 3c, then minus 1x. And then the last one will be a positive 3. Wait, was it negative or positive? Where am I looking? Oh, no, that should have been a plus. I don't know why I put a minus. My mistake. We good? All right. So we know that 2c plus 1 needs to equal a. So we can't use that one. We know that c minus 5 needs to equal the negative 3. So there we go. So c is going to be 2. So if c is 2, then that means that 2 times 2 plus 1 is equal to a. So a is 5. Awesome. And then I know that negative 3c minus 1 is equal to b. And since c is 2, that's negative 3 times 2 minus 1. So b is, there we go. Good stuff. All right. So moving forward, we have division, long and synthetic. This is a review. You guys did long and synthetic division back in algebra 1, algebra 2. You did it in pre-cal. Okay. So this is just recapping that if you have a polynomial function and it's being divided by a linear factor ax plus b until you're left with a constant remainder, which is r, then basically your result is written like so. Okay? Where q of x represents your quotient, r is your remainder, and then a plus b was your divisor. Because remember, you should have written it as the quotient plus the remainder divided by the divisor. You should never put the r colon and then the remainder. You should never have done that. That is the proper way to write, dividing a polynomial. Okay? Do realize is that if you multiply the quotient by the divisor and add the remainder, you should always get your original polynomial function every time. Okay? Same thing applies when you're dividing a polynomial by a quadratic. Your result is the quotient plus your remainder, which would be an expression. Okay? Your remainder would be an expression whenever you divide by a quadratic, unless it went in evenly, unless it was actually like one of the factors. Okay? Remember this? Yes, no? Okay. Well, then let's see. Okay? We perform the division of x to the fourth plus 2x squared minus 1 all over x plus 3. We're going to do this. We'll do it. This one we can do synthetic because at some point we are going to have to use long division. So we'll review both of them. Okay? Remember synthetic division. That's when you have the backwards L. What went in the backwards L?
The negative, well, you're on root, so -3.
It would be the root. So technically, it's basically saying that this right here, that x plus 3, is a factor, and so you would solve that to get -3 there. What went beside the backwards L?
The coefficients plus placeholders.
Exactly, your coefficients of your dividend. Of course, if any of the terms were missing, like in this case, you're missing an x to the third term and you're missing an x term, you put in your placeholder. So this will be 1, 0, 2, 0, and -1. And then, recalling from a synthetic division, what do you do?
Drop down your first term and then multiply it by the -3.
Mm-hmm.
The product goes under the 0 you have them.
Exactly.
Keep repeating.
Always drop down your first term, and whatever's underneath the line, you multiply by your root. So then that'll be -3, and you continue that process with 0 plus a -3. Keep going. 9, 11. Uh-huh. And 98 represents is your remainder. 98 is your remainder.
98 over x plus 3.
Yep, but they want us to write it in this particular form. So what is our quotient? What is our quotient?
X to the third minus 3x squared plus 11x minus 33.
Very good. That gets multiplied by your divisor, which was x plus 3. Then you subtract your remainder, and that is our result. Add it. My mistake, because it was a positive 98. Y'all remember this? Last time memory lane? Cool deal. Alright? Let's do this one. It says carry out the division and hence factorize the numerator into linear factors. Okay? Once you carry out the division, you're going to be left with a what? Like when you divide that numerator by an x minus 3, what are you going to be left with? You're going to be left with a quadratic, which means that since it's said to factor the numerator into linear factors, once you get that quadratic, you should be able to factor it. Okay? So I want you guys to go ahead and divide this cubic by this x minus 3. Get that quadratic, and then I want you to factor that quadratic. So dividing this out, you should have had 3, then 2, -1, -13, and -6. Bring down the 2. Should have been 6, 5, 15, 2, positive 6 with a remainder of 0. So yes, this was a quadratic of 2x squared plus 5x plus 2. Then you had to factor that. What did it factor to be?
2x plus 1, x plus 2.
And since it said to then hence factorize the numerator to its linear factors, both of these are linear factors, and the last one is x minus 3. Very good. Okay? Let's take a look at this one. We're going to find the quotient and the remainder for this particular polynomial division, and then we're going to write it in that respective form. Now this one, you would have to use long division. To be honest, you can use long division for any polynomial division, because long division is like what quadratic formula is when you're solving a quadratic. It works every time. Synthetic only works for linear factors that are in the form of x plus a. Okay? There's nothing in front of the x. Okay, that's the only time it can work. Long division is always a go-to, surefire, works every time. Okay? So, long division requires that division bar. Y'all remember that? The divisor goes on the outside, so that's x squared minus x plus 1. Of course, if there are any placeholders, you put those in there as well. And then the dividend, which is the numerator, goes on the inside. Do I have any placeholders?
Yeah. For the x squared.
And the process of doing the multiplication, I don't know who taught you how, but how I teach my students is I say, you ask yourself, you look at the very first term of your divisor, and you say, what times x squared will give you x to the fourth. And that is a what?
X squared.
That is an x squared. So that's going to be x squared on the top. Me, I am visual. I like to line my stuff up, so I always will put any terms like on top of the other. And then you multiply that x squared, that result that you get by the entire divisor. What's x squared times x squared?
X to the fourth.
What is x squared times negative x?
Negative x to the third.
And what's x squared times 1? And because it's old school long division, you always remember that you have to do what at this point? Subtract. When you subtract this entire result, you basically are changing the signs of every single term. So this becomes a minus 4x, a positive x to the third. I'm sorry, it becomes a negative x to the fourth, a positive x to the third, and then a negative x squared. Terms should be canceling out as you do this. So then you're left with a 5x to the third minus x squared. What do you do from here?
Drop down.
What?
Yeah. Negative.
Drop down the rest of it.
You drop down not the rest of it, just the next term. And then you repeat. What times x squared will give you 5x to the third? 5x. So that's a plus 5x. And then you multiply. 5x times x squared.
I think 5x squared.
5x3.
Oh wait.
Because yeah, it's 5x to the third. So 5x to the third was negative x times a negative x times a 5x.
Negative 5x squared.
And what's a 1 times a 5x?
Plus 5x.
And you have to remember to do what?
Change the signs.
Switch your signs. So then this becomes a negative 5x to the third, a positive 5x squared, and then a negative 5x. Again, terms cancel out, and I'm left with 4x squared,
Minus 6x squared plus 1.
4x squared minus the 6x,
When you bring down 1?
and then you bring down the 1. Yeah, you said it's 6x squared. One more time for the good time. What times x squared gives me 4x squared?
4x.
No,
4.
just 4.
Just 4.
Because it's the x squared is the first term in the divisor. So 4 times x squared is 4x squared. 4 times negative x is a positive or negative.
Negative positive.
And then 4 times 1 is 4. And you must remember to switch your signs. What's my remainder?
Negative 2x minus 3.
Negative 2x minus 3. So I write my result as my quotient, which is x squared plus 5x plus 4 times my divisor plus my remainder, which is a negative 2x minus 3. So that's going to be a minus 2x minus 3. We haven't forgotten, have we? Keep it going. Division of polynomials lets us know which one of these divisors are actually indeed factors of our polynomial. Okay? Another way that we can actually determine whether or not it is a factor is by using the remainder theorem. So when a polynomial is divided by x minus k, a linear factor, until a constant remainder r is obtained, then r is equal to p of k. R representing the remainder, k representing the root or the zero from that factor, and then so p of k would be you plugging in that value into your polynomial. Okay? Do realize again that if you have a linear factor times your quotient plus your remainder, it equals your polynomial function. When you plug in a particular root into your polynomial, it will equal your remainder. And then if your polynomial is divided by that factor, it will leave you with your remainder of r. Okay? Just a couple of things to remember especially when it comes to like those general questions where it actually maybe define a random variable, like an A or a C, and polynomials are being divided. Okay? Question? Starting off simple. We're going to use the remainder theorem to find the remainder when x to the fourth minus 3x to the third plus x minus 4 is divided by x minus 2. Remainder theorem is basically, to get your remainder, you evaluate your polynomial at that particular root. What is the root here? Negative 2. So that means you're going to plug in negative 2 in for every x of that polynomial to get your remainder. What's negative 2 to the fourth power? What's negative 2 to the third power? Negative 3 times negative 8. So I have 16 plus 24 minus 6, just combining a few things as I go. What's my remainder? 34. Simple as that. Okay. Easy problem. Using remainder theorem. Since the remainder is not, never mind, jumping ahead. When x to the third plus 4x squared plus ax plus b is divided by x minus 2, the remainder is 20. And when it's divided by x plus 5, the remainder is 6. We have to find a and b. We have to find a and b. So since I know the remainder is 20 when the polynomial is being divided by x plus 5, that basically means that 20 would equal p of what value? 2. Remember, when your remainder is equal to p of k, if your remainder is 20, that means that k was what? Okay, let's go back real quick. All right, remember on this one, we set it up like so. To find your remainder, you evaluate your polynomial at k. So for this particular problem, we were looking for our remainder, so we plugged in what value? We plugged in negative 2. Where did the negative 2 come from? From where? This x plus 2, once you set it equal to 0 and you would solve, you get your negative 2. So p of negative 2 gave us a result of 34. 34 is the what? Remainder. So I really could say that 34 is equal to p of negative 2. Okay? So applying it back here to this problem, if the remainder is 20 when the polynomial is being divided by x plus 5, then 20 is equal to p of?
It's being divided by x minus 2.
Oh, sorry. Sorry. You're right. My bad. My bad. Okay. So, since I know that, we can pretty much set up the equation. That's 20 equals 2 to the third, which is 8, plus
4 times 16 is 64. Wait, no. That's 2, 4, and then 16. Yeah.
So it'll be 16 plus, this will be a 2a plus b. Following a similar pattern, let me read this all the way through again. It will be 6 is equal to p of negative 5. Again, I apologize. So then that'll be 6 is equal to, what's negative 5 to the third power? Negative 125. And then what about 4 times negative 5 to the second power? What is that? Positive or negative? Positive. Minus 5a plus b. you're trying to find the values of A and B. I have two equations with two variables, and I could do systems of equations. Yes. If I combine 8 and 16, that gives me 24. I can subtract that 24 over to get negative 4 equals 2A plus B. That's one of my equations. And then over here, if I combine, that gives me a negative 25. When I add it over, that gives me 31 equals negative 5A plus B. And I have my second equation. So yes, I can do a system of equations. Okay? It doesn't specify row operations, so I'm going to do this using whichever method I feel more comfortable with. Go ahead, I'm going to use elimination, change this to a negative, change this to a positive, change this to a negative. So that's going to give me negative 35 equals 7A. So A equals negative 5. And since A equals negative 5, I can plug that into one of my equations, either 1 or 2. To find that negative 4 is equal to 2 times negative 5 plus B. And B is going to equal 6. Questions? Give this one a try. When a polynomial is divided by x squared minus 3x plus 7, the quotient is x squared plus x minus 1, and the remainder is unknown. However, we're told that the remainder is written in the form of ax plus b. Remember, from before, if you have a polynomial function, it's equal to your quotient times your divisor plus your remainder, right? What's your quotient? What's your divisor? And our remainder is what? It is unknown, but it's in the form of what?
Ax plus b.
So you have your polynomial here that you can use the same way we've done the last two problems. And we're told that when it's x minus 2, the remainder is 29. X plus 1, the remainder is negative 16. We can use that to find the value of A and B, hence our remainder. So that means that 29 should equal the remainder when I plug in what value for x? When I plug in 2. What's 2 squared? 2 squared is 4 plus 2. 6 minus 1. 5. So I plug in 2. Plug in 2 again. What's 2 squared? What's 3 times 2? 6. So it's 4 minus 6 plus 7. So the same way we did it before is that this time you needed that one of the other features or important things to remember to set it up. So then the next one would be negative 16 has to equal the remainder when the polynomial is evaluated at what value? What number? Negative 1. Negative 1 squared? Minus 1? Minus 1. All I'm doing is plugging negative 1 into my polynomial. Negative 1 squared? Negative 3 and negative 1 make a positive 3. So what's 1 plus 3? Plus 7? And then you have the system again that you can find A and B. Okay, find A and B, then write my remainder. So you basically have 4 equals 2A plus B, and you have negative 5 equals negative A plus B. I went ahead and eliminated b just by changing the signs. So then that gives you 9 equals 3a. So a is 3. And then b was the -2 once you plugged it back in. So my remainder is 3a minus 2. Ooh, not 3a. Questions? So, realize that for any polynomial, okay, if k is a 0 of a polynomial function, if and only if the remainder, if and only if the factor x minus, or oh my gosh, okay. For any polynomial, phi of x, k is a 0, a root, a solution of a polynomial if and only if x minus k is a factor of p of x. Alright? So if you happen to get a remainder of 0, that means that k minus x was a factor of that polynomial. Okay? Y'all remember that? From division and factors and things like that? Okay? So don't forget about that as well. In this example, you're asked to find k, given that x minus 2 is a factor of that polynomial. Since you already know that x minus 2 is a factor, you automatically know the remainder should equal 0. So you use that piece of information to help you find the value of k. Once you find the value of k, you're able to do the division to get the quadratic so that you can fully factor that polynomial. Okay? So, since you know that x minus 2 is a factor, that means that p of 2 should equal 0. The remainder should be 0. So when I plug in 2 and set it equal to 0, I'll be able to solve for k. So that becomes 2 to the third plus 4k minus 6 plus 6. 2 to the third is 8. So this becomes 8 plus 4k, because and the 6's cancel out. K, 4k equals -8. K is -2. Again, we would know that again because it's a factor, the remainder has to equal 0. Now that I have my polynomial function, I can divide it by x minus 2 to get the remaining quadratic, which I can factor from there. What goes in the backwards L? And why can I use synthetic division here? It's a linear factor and it's in the form of x minus or x plus a number. Bring down the 1. 1 times 2. -2 plus 2. 0 times 2. -3 plus 0. -3 times 2. And it should work out that way. If you end up getting a remainder that's not 0, that means you found the wrong number. It told you it was a factor, so that meant the remainder had to be 0. So my quadratic that I'm left with is x squared minus 3. But it's asking me to fully factor this.
You can do x plus 3.
Close.
Square root of 3x minus the square root of 3.
Exactly. If I wanted to keep solving this out, I would find out that my zeros were plus or minus the square root of 3, which means that when I write my factors, that is an x minus square root of 3 and an x plus square root of 3. And then I can't forget the original factor that was given to me, which was an x minus 2. And that is the fully factored form. And look at one more example. So, what we talked about so far, okay? If you have a polynomial that has a degree of n, then that polynomial has exactly n zeros, Okay? So if your polynomial has a degree of 4, then that means it has exactly 4 zeros, each of which can be written in the form of a plus bi, where a and b are real numbers, and some of them could be repeated. Some of your zeros could be repeated. Now do realize that it says the form of a plus bi. Yes, that's like a complex number. It's like saying imaginary. But b could be very well 0, and you're still left with the real part. Okay? So a is real, the bi part is the imaginary. So it suffices for all zeros, real and imaginary. Okay? Also, every real polynomial of degree n can be factored into n complex linear factors. You saw from the last example, we were able to factor it down into linear factors. Okay? We could do that with several of them. Okay? Every polynomial can be expressed as a product of either linear factors and or real irreducible quadratic factors. Those are the ones, think from the very first example that we did, when you had the x minus 2, the 3x plus 1, and then you had that quadratic, which I think was like x squared plus 2x minus 4. This is an example. Okay? So every real polynomial can be expressed as a product of linear factors and irreducible quadratic factors. All right? Could actually probably broken that down some more and then wrote it as the imaginary factors as well. Lastly, every real polynomial degree n has exactly that many zeros. As we said, if p plus qi is a 0, then we know its conjugate, p minus qi, is also a 0. All the imaginary ones we dealt with had its original and its conjugate. And every polynomial of odd degree has at least one real 0. And we talked about that Tuesday. You remember that example that I drew, like literally right here in this general area? And I was like, no, this will always hit the x-axis because this is an odd degree polynomial. However, even degree polynomials could very well
Always be imaginary.
They could possibly be imaginary. Okay? So, suppose negative 3 plus I is a 0 of that polynomial where a is real. Find a and then hence find all the zeros of this cubic. So go ahead and do that now. You can do it on your desk. So we're going to incorporate like everything that we've done like so far with polynomials this week. Okay? If you know that negative 3 plus I is a 0, then you also know what is a 0. Negative 3 minus I, okay? So that's 2 out of your how many zeros you should have? You should have 3 of them, so that's 2. So we really just got to find that one last one, okay? So that's the root. Negative 3 minus I is the root. Then we have another linear factor that when we solve it's going to give us our other root, okay? So I see a lot of you guys doing the whole writing it as the factors and multiplying to get the quadratic, when remember the sum of the roots is equal to negative b over a, and then the product of the roots is equal to c over a. Don't forget that. In my opinion, I feel like it's a lot easier than trying to go through and multiply with the three term factors, okay? Because this becomes a negative 6, and when I multiply this, negative 3 times negative 3 is 9. So you have a negative I squared, which is basically saying plus 1, which is 10. So you'll get your quadratic of x squared plus 6x plus 10. Okay? That times another factor should equal ax to the third plus 9x squared plus ax minus 30. Now, if your variable is somewhere else than other than in that polynomial, you could have done division to get the other factor, but this x squared plus 6x plus 10 needs to be multiplied by something to get us that. What was going to go in that blank? What can go in that blank? A little louder, I can't hear you back there.
A little, an AX.
An AX, yes. Because think about it, that first term has to be an AX to the third. We already have an X squared, so then it has to be an AX. And since we know there's only one more zero, we know this part has to be a linear factor. So this is going to be AX plus a number, AX minus a number here. What number is going to be at the end?
-3.
And how do you know -3?
Because 30 is your constant.
Has to be times to the
30 is my constant, so 10 times something got to give me -30. So now that I know that, I could multiply that left side and then do what we did on the other problems. So this would be AX to the third Okay. When I combine my like terms, this will give me a 6a minus 3x squared, and then a 10a minus 18x. The one that I need is this one right here with the x squared, right? So 6a minus 3 equals 9. 6a equals 12. A is what? A is 2. So I found A. So A is 2. Now it says to find all the real zeros of the cubic. Well, I already know 2 of them. The third one came right here, where AX minus 3, or in other words, 2x minus 3 needs to equal 0. What's my last one? So 3 over 2, -3 plus or minus I. And those are my zeros. Got one more. Try to do this one. Start you off, okay? Talked about on the previous slides. Remember, if you have a 0, it's written in the form of A plus BI. And I said that it doesn't always have to be an imaginary number, because the A represents the real part, where BI represents the imaginary part. So when it says that 1 0 is purely imaginary, that means that it's purely, solely just the BI. There is no real part to it. Just the BI. So using that, try to see where you can get to find the value of A and then the zeros of the polynomial using that. So one root is BI, the other root is what? Okay, remember, you can always find a quadratic from two complex or two roots by doing what? Adding and multiplying. So when I add them, which is pretty much this right here, what do you get? 0. So that means that 0 is equal to negative b over a. What about when I multiply them? What do you get?
Negative b.
B squared and I squared.
Which is?
Positive b squared.
So that's equal to c over a. So what's the quadratic?
So
X squared plus b squared. Okay? There you go. Now this is a cubic polynomial, which means I should have how many zeros?
3.
3. One is bi. Don't know what it is yet. Negative bi. And so there's one more 0 to be found. So that means it has to be a linear factor. That when I multiply them together, it's going to give me ax cubed plus a plus 1x squared plus 10x plus 15. How can I get an ax squared? I'm sorry, an ax cubed. I apologize. An ax. How can I get that constant 15 when I have a b squared?
Yes.
Don't overthink it. what can I multiply b squared by to get a 15? What you say, Logan?
I said 15 over b squared.
And that's exactly what it is. Think about it. B squared times 15 over b squared. B squares cancel out. You got your 15.
Oh.
So foil that. Find which piece is going to help you get to the value of A and also B, so you can actually find what your imaginary zeros are.
This is quirky.
So foil.
Oh.
B squared times 8 equals 10.
And distribute correctly. A is equal to 2. So when you FOIL this out, of course you match up your terms. 15 over b squared is equivalent to a plus 1. ab squared is equivalent to 10. And you basically are solving a system using substitution. What I did was I went ahead and solved the second equation for b squared. So that way I could plug it in over here. It probably wasn't of course, there's different ways that you could have done this. Probably easier, who knows. But this is how I saw it first. I plugged in 10 over a for the b squared into the equation on your left. I multiplied both sides by a to get rid of the denominator, distributed the 10 over correctly the second time, and then got that a is equal to 2. Okay? Since a is equal to 2, I'm able to find my zeros. Okay? Because if a is equal to 2, I can plug it into this equation that you see here to find b. I need b to find my imaginary zeros. So that's 10 over 2 is equal to b squared. So b is equal to what? Plus or minus square root of 5.
What?
Wait, no, I missed it somewhere.
What? What?
Yeah, so right there.
What? Huh?
Okay.
I found a, and the rest of the question said to find the zeros of the polynomial.
Okay. So
Okay? So I needed to figure out what were my b here, because those were my imaginary zeros. So I made a mistake somewhere. I didn't mess up. I just forgot to add the I. So then it's be the square root of I, negative I, square root of 5, and the last zero would be, what will be the last zero? Negative 3 over 2. And you get that last zero from this point here. When you plug in A, since we know B is a plus or minus square root of 5, when you square it, it still just gives you 5. So then that's 2x plus 3, and you get a negative.